All right, let's dive into a really classic physics puzzle today. We're cracking open I.E. Irodov's Problems in General Physics, which, if you know it, is legendary for its brain-bending challenges. We're going to tackle problem 1.169, which is all about collisions. But we're not just going to find the answer and call it a day. No, we're going to really break down the strategy so you can see how to use core principles like conservation of momentum and energy to solve pretty much any mechanics problem that comes your way.
So here's the big question, the central puzzle. Imagine you see two particles crash into each other. One hits the other, they scatter, and they fly off. Now, if the only thing you can do is measure their speeds and the angles they fly off at, is that enough information to figure out the ratio of their masses? It seems like it might not be enough, right? But you're about to see how physics gives us the perfect set of tools to do exactly that.
Okay, here's the official problem statement. We have particle 1, and it smacks into a stationary particle 2. And notice this key phrase, it's a perfectly elastic collision. That is a massive clue, and we'll come back to it. Our mission is to find the mass ratio, m1 divided by m2. And we have to do this for two totally different scenarios. Part A is a simple head-on crash. They just fly apart in opposite directions. Part B is more of a glancing blow, where they scatter off at a 60-degree angle to each other. Every one of these little details gives us a piece of the puzzle.
Before we even think about writing a single equation, let's get our toolkit ready. For basically any collision problem you'll ever face, there are two fundamental, unbreakable laws of physics that are going to be your guide. These are the absolute, non-negotiable rules of the game.
First up in our toolkit, conservation of momentum. This principle is simple. The total amount of oof, or mass in motion, that you have before a collision has to be the exact same amount you have after. But here's the crucial detail you can never forget. Momentum is a vector. It has both a size and a direction. And that little fact is going to be the absolute key to cracking part B of this problem.
And here's our second tool, which comes directly from that special phrase in the problem, perfectly elastic. When you see that, it's like a giant flashing sign. It means the collision is perfect. No energy is wasted as heat or sound. The total kinetic energy you have before the crash is exactly equal to the total kinetic energy you have after. And that gives us a second incredibly powerful equation to work with.
All right, toolkit assembled, let's get to work on part A. This is the more straightforward case, a one-dimensional head-on collision. You can just picture one billiard ball hitting another one dead center. We're going to use a nice, clear, step-by-step plan to knock this out.
So here's our game plan. Super simple. First, we'll write down our two main equations from our toolkit, one for momentum, one for energy. Second, we'll plug in the specific details from part A, namely that the particles fly off with equal and opposite speeds. And third, we'll just let the algebra do its thing until we've solved for that mass ratio we're looking for. Easy as that.
And here are those two laws written out in math speak. On the left, we've got momentum conservation. The initial momentum of particle 1 has to equal the sum of the final momenta. And on the right, kinetic energy conservation. The initial kinetic energy of particle 1 equals the sum of the final energies. All the physics we need is sitting right here in these two expressions.
Now for step 2, plugging in what the problem tells us. For part A, we're told the particles fly apart with equal speeds, but in opposite directions. So this is easy. Let's just say particle 2 flies off with some velocity, we'll call it v. That means particle 1 has to recoil with a velocity of negative v. So we're going to take these two facts and substitute them directly into our conservation equations. And hey, just a quick heads up, this is a super common trap students fall into. With velocity, the direction, the plus or minus sign is everything. It is so easy to mess one up and have the whole solution go wrong. So let's be crystal clear. We'll say the initial direction of particle 1 is the positive direction, and we'll stick with that convention the whole way through. A little careful bookkeeping now saves a world of pain later.
Okay, let's put it all together. After we substitute our conditions, the momentum equation simplifies, and so does the energy equation. Now here comes the clever trick. We rearrange both equations to solve for the final speed. The momentum equation gives us an expression for v, and the energy equation gives us one for v squared. So we just square the result from our momentum equation and set it equal to the result from our energy equation. And when we do that, poof! All the velocity terms completely cancel out, leaving us with a beautiful, simple equation that only has the masses in it. We do a little cross multiplication, tidy it up, and we get our answer. The mass ratio, m1 over m2, is 3.
All right, part A's done. Now for the real fun, part B. This is where your understanding of vectors gets a true workout. The collision isn't head-on anymore. It's a glancing blow. It's a two-dimensional problem now. And yeah, it looks a bit more complicated, but trust me, our fundamental toolkit is all we need to solve it.
Our roadmap for Part B has one very important extra step right at the beginning. Because we're now in 2 dimensions, we absolutely have to break the momentum down into its x and y components. Once we've done that, the plan is pretty much the same. Write the conservation laws, use the angle the problem gives us, and solve for the mass ratio.
This is exactly why we made such a big deal about momentum being a vector earlier. You can't just compare the total momentum before and after anymore. You have to make sure that the momentum in the horizontal direction is conserved and that the momentum in the vertical direction is conserved, separately. It's like you have to balance 2 different checkbooks, one for the x-axis and one for the y-axis. This lets us turn one complicated 2D problem into 2 much easier 1D problems.
So let's see what this looks like. And check this out. This is the really cool part. Look at the y-axis, the up and down motion. Before the collision, everything is moving horizontally, so the initial y momentum is just 0. Now, after the collision, the problem tells us they fly apart symmetrically. That means their up and down velocities have to be perfectly equal and opposite, canceling each other out. So the final y momentum also has to be 0. From that one simple fact, we can immediately see that m1 times v1 prime has to equal m2 times v2 prime. And that, right there, is a massive shortcut that the symmetry of the problem just handed to us.
And now for some good news. Remember kinetic energy? Unlike momentum, it's a scalar. It has a size, but it doesn't care about direction. What does that mean for us? It means we don't have to break our energy equation into components. Phew! It looks exactly the same as it did in Part A, which keeps the math a whole lot cleaner.
So now we've got our system of equations. We have our x momentum conservation, we have that great little shortcut we got from the y momentum, and we have our kinetic energy equation. We know the angle between them is 60 degrees, so each one scatters at 30 degrees from the center line. We use our shortcut to substitute for one of the velocities, we do a bit more algebra than we did for Part A, and when the dust settles, we find our final answer for Part B. The mass ratio m1 over m2 is exactly 2.
So there you have it. The answers are 3 and 2. But honestly, the numbers themselves aren't the real prize here. The most valuable thing we've done is develop a repeatable, powerful strategy. So let's just quickly recap this method, because this is the process you can use for so many other physics problems. So, what are the big takeaways? First and most importantly, always start with the conservation laws. They are your rock. Second, always be on the lookout for keywords like elastic or inelastic. They give you extra tools. Third, if you see a problem in 2D or 3D, your first instinct should be to break that momentum down into its components. And finally, always hunt for symmetries in the problem. They are often secret clues that will make your math a whole lot easier.
You know, the crucial point is this. No matter how messy or complicated a collision might look, it's really just a story about 2 things, momentum and energy. If you can master applying these 2 conservation laws, you're on the right track to solving almost anything. They really are the master keys to the world of mechanics.
And I'll just leave you with one final thought to chew on. What if the problem changed just one single word? What if the collision was inelastic, and the 2 particles actually stuck together after they hit? Which of our 2 master keys, conservation of momentum or conservation of kinetic energy, would still work? And which one would we have to throw away? Thinking that through is a fantastic next step on your physics journey.